distance, and yada, yada, yada. But let me just kind of tell you what it is. Say we have some initial state, psi. You can think of this as like a wave function in position. Okay? We let it evolve with a Hamiltonian that has the parameter omega. At some time later, we'll get some final wave function. Okay, so we just propagate this forward and get the final wave function. Now we want to see how does this final wave function compare to if we start with the same state, we evolve with h of omega plus d omega. What kind of wave function do we get later on? Now, if these wave functions are exactly the same, then there's no quantum Fisher information. But if they're orthogonal, then there's a maximal amount of quantum Fisher information. So that's what this Burius distance says. It says, it's like 1 minus the overlap of these two wave functions. If they're non-overlapping, then there's maximal quantum Fisher information. And if they are highly overlapping, then there's very little quantum Fisher information.
I should probably know this, but I'm forgetting. What is the information here? We're using this Fisher information, but when you say more Fisher information versus less Fisher information, what the information is about the...
So the information...
How sensitive it is to this parameter omega?
So it's like in each measurement, how much information does it convey? So if you go back to this Kramer-Rao bound, right here, the variance is always going to be greater than or equal to 1 over the amount of data. So like if you're using, say, do the experiment over and over and over and over again, the fluctuations average down like square root of the number of repetitions, okay? So that's that piece. The other thing is like how much information does each measurement contain about the thing you want to know? Okay, so and this is intuitive. You're making a measurement, you're going to try to find some way to be really sensitive to the parameter you're interested in so that you get the most information. It's just as a way to quantify what that information is. Okay, in the quantum case, it's just sort of a generalization of that to involve quantum states. So I will give you an example. I think that's exactly what I'll do right now. So let's go back to this example of the cesium clock. The cesium clock, remember, we're measuring the frequency difference between the ground state and the excited state, or these two hyperfine levels. It's a two-level system. So 2 quantum levels, I'll think of it as a quantum bit, a qubit. Okay, so we think in the language of qubits, but this could be anything, just measuring the energy difference between any 2 levels of a system. So very general. So we want to measure the transition frequency of this qubit. So let's just think about what states of this quantum bit would maximize the quantum Fisher information. Okay? So let's start with the ground state. Is that a good state for maximizing the quantum information? The idea is we'll take the ground state, we'll propagate it forward. Uh-oh, I ran out of battery. Oh, there we go. With frequency omega. So the Hamiltonian involving with some sort of frequency. So it's just processing on the z-axis. And then we can try it with a slightly higher frequency. It processes even more. But you can see these 2 states are exactly the same. So this ground state has no quantum Fisher information about the energy difference. So it's a terrible way to measure the frequency by leaving the qubit in the ground state. But that's obvious to people who've done Ramsey measurements or know how to measure frequency differences. But this makes sense? Is that?
Sorry, I think I missed something. What is evolution with omega and evolution with omega plus omega?
So it's going to evolve under the Hamiltonian with frequency omega. So the Hamiltonian is just sigma z over 2 or something, right? It just has that much energy.
Yeah.
Okay, so it's just going to process around the z-axis, and it processes a little faster, a little slower, but it's not going to change the state. So as you might know, the way you measure the frequency difference, and this is how it's done in the cesium clock, is with a superposition state. You make an equal superposition of the ground and excited state. Okay, that's something like here on the equator of the Bloch sphere. Then when it evolves with omega, it processes around the z-axis, and now you can see it change, moves around like this. And if we change the frequency, it moves around like this, and now the 2 states we end up with are different. So this will have non-zero quantum Fisher information, and that's, of course, that's why you use superposition states to measure the energy difference between two levels.
Is there a bound quantum Fisher information?
There is a bound, and I'll actually tell you what that is on the next slide, probably. Good question. So what is the maximum quantum Fisher information you can expect to get? And the idea to showing this, and I can't really give you a full derivation of it, partly because it's a little beyond me, and partly because it would be really technical. the idea is we want to consider the eigenvalues of the derivative of the Hamiltonian with respect to the parameter you're interested in. The idea is just like on the last slide, here we're going to take it, we're going to evolve it forward to some Hamiltonian or a slightly different Hamiltonian. Then we want to see basically how much do the states change as we change the Hamiltonian. And ultimately this boils down to thinking about the difference between the maximum and minimum eigenvalues of the derivative of the Hamiltonian with respect to the parameter you're interested in. So we want to consider the eigenvalues of this derivative, and the Fisher information is kind of given by the difference between the eigenvalues of the Hamiltonian. If you really want to think about it, you can think you have this unitary operation evolving under a Hamiltonian. You're going to break that into little sequences of little steps where you can say, so think about maximizing the Fisher information at each step in time, and you end up with some expression that kind of looks like this.
So it's kind of a susceptibility. Okay.
Sure.
I mean, you're basically trying to create a wave function or an initial wave function which will change maximally with the change of parameter you want.
That's right. Absolutely.
But at the ground state or the excited state, nothing happens. And at 50 superposition,
Yeah.
what seems to happen.
So exactly, absolutely. And so in the case of this energy difference measurement we're interested in, irrespective of what states we choose, we can just sort of think about what is the best we can do, and it's going to be by maximizing the difference between these eigenvalues. So we want to sort of choose states that are either that are some sort of superposition of these eigenvalues. Maybe that's not going to fly. Yeah.
So according to the sphere picture,
Yeah.
so the information is not directly proportional to the maximum displacement of the vector, right? It's not directly proportional. Otherwise, it would have been always the 50-50 superposition states.
So it's directly proportional to how separated the states are, how separated they become when evolving with different frequencies or by changing whatever parameter you want. You just want to see how different do the states get. If they're perfectly orthogonal, then you've maximized your Fisher information. And if they're still overlapping, then you don't have as much Fisher information.
I think he's asking for the operational definition. Is it the distance in the block sphere, or is it basically this overlap function?
It's this overlap function. It's multiple slides back. It's really this thing here. And there's lots of different ways to express this, but it's really this overlap function. So it's not distance in the block sphere, although that is going to be close to this for small changes especially.
So the idea, I would think that in the block sphere, if it is 50-50 superposition state, then it is the maximally information.
Yeah, that's right, and that's true. And actually, I'll show you here. So if we go to our case where we're measuring this energy difference here, so we want to. I told you this is sort of the maximum you can do. So we take the derivative of the Hamiltonian with respect to the frequency. That's just sigma z over 2. So the eigenvalues of this are just plus or minus a half. So then I'm going to integrate dt up to t. So the quantum Fisher information is going to go like t squared, which means that the frequency difference, which is going to go like, well, the frequency variance goes like 1 over t squared. So the frequency uncertainty goes like 1 over t. So this just recovers what I told you at the beginning, that your frequency sensitivity goes like 1 over t. And this is actually the best you can do for a static Hamiltonian. If your Hamiltonian doesn't depend on time, then when you take the derivative with respect to your thing, you'll just get a constant. You're integrating a constant up to some time. You're just going to get a quantum Fisher information that at best proves as t squared. And your sensitivity goes like 1 over t.
Yeah, that just depends because here you only had one factor of omega in front of the sigma z.
Oh, so you could have other factors of omega and so forth. And those will give you different eigenvalues, and then you can think you'll be more sensitive at higher frequency than lower frequency and so forth. But the scaling with time, which is kind of what I'm interested in, is always going to be 1 over t.
Is this a statement that's specific for this Hamiltonian or any Hamiltonian?
This is true for any Hamiltonian. Any Hamiltonian that does not depend on time, the uncertainty in any parameter at best improves like 1 over t. Okay? But the fact that I'm talking about this sort of thing, you could think, okay, what if the Hamiltonian happened to depend on time? Then this might not be true. You might be able to do better, or you might do worse. That's what we'll find out. So let's think about a time-dependent Hamiltonian. What I have in mind is we're going to take the energy difference of this qubit, and we're just going to shake the level up and down. And that's the frequency we want to measure. We're going to measure the frequency of the modulation of the energy. If there's a spin half particle, you just put a oscillating magnetic field in there. So this is very general to have some sort of time-varying Hamiltonian. Okay, so this is the Hamiltonian. It's the energy in the appropriate rotating frame. It just goes like sine of omega t. So let's think about what the maximum Fisher information is in this case.
Maybe this is not written exactly. Is it a sine omega t or is it some 1 plus?
Oh, yeah, so plus some omega naught, if you want to think about it in the lab frame or something. But I'm just going to think about, yeah, so there's going to be a 1 plus, but we can just go into a frame rotating with the mean value of this. Okay, so when you take the derivative with respect to omega, we pull out an extra factor of time. So when we look at the eigenvalues of this, of the derivative of the Hamiltonian with respect to omega, they look like this. I've plotted them for you. So the positive eigenvalue goes, up like this, and then the cosine becomes negative, so they oscillate, and they grow in time. So the negative 1 goes like this, so forth and so on. Okay, so the maximum quantum Fisher information is going to be related to, or it's given by the integral of the difference of these two. But you can see the difference of these two is, so it's positive here, but it's negative here, then it's positive here, then it's negative here. So sort of the integral cancels itself out at different times. So here's the quantum Fisher information as a function of time. Grows, but then it goes down to 0 when this integral reaches 0, and then it grows again, and so forth and so on. So you still get the quantum Fisher information scaling as t squared, which is what we had before. But what if we could somehow flip the sign of these eigenvalues at each point in time here? If I apply some sort of control that now makes it the positive one always stays on top and the negative one always stays on the bottom, then this integral would always be growing, and it would grow actually like t to the 4. Sorry. Okay, so that's what we want to do. In this case, you could have quantum Fisher information that's growing much, much faster than when you would get in any other case.
Why are they not still zeros?
So they're not still zeros because, so you can see there are inflection points, or there are points where the quantum Fisher information is not growing. That's where this is sort of crossing 0. But this is always, so now I'm just sort of adding up the area of the green minus the area of the blue. But previously, I had alternating green and blue on either side. Okay? So in that one case, the integral changes sign. We're taking the square of it. But in this case, the integral doesn't change sign. It's always increasing. Okay?
You're saying the envelope process is.
So when I don't do this and then they alternate, it oscillates in time because every once in a while the integral is changing sign. We're just squaring it. So this is the square of some growing sign or something. But when we have control, this integral is always positive, so it just grows. It's t to the 4.
Wouldn't you want the precise value of omega beforehand follow the control?
Oh, what a good question. Save that question for, I'll point to you in a little bit, and then you can ask that question, okay? Good. So neglecting that, let's just keep going. So let's try to do this. All we have to do is figure out what this control is that changes these eigenvalues, and sort of see that we should see that the quantum Fisher information increases much more quickly. That is, the frequency sensitivity improves like 1 over t squared. That's the best you could possibly do, actually. Okay, so here's the idea of experiment. This is the first time we'll mention what we'll do the experiment with, because everything we've talked about so far is very general. You could do this with an atomic system. You could do it with spin in a magnetic field. So what we're going to do is use one of these transmon qubits. You don't have to know what this is. It's just a 2-level system. And so we're going to apply this. So basically, we'll prepare a superposition state. We'll apply this time-dependent Hamiltonian, and then we'll measure sort of the accumulated phase by applying another rotation and projecting onto the energy axis. So you can think of how it's evolving. It's just sort of wiggling back and forth as we change the magnetic field, as we change as the Hamiltonian changes. Okay, so then we let it wiggle back and forth, and at some time we measure the accumulated phase. And what we do is we do that by rotating along the appropriate axis so that we rotate orthogonal to what the phase is. So we measure sigma z, which just gives us the phase, whatever. So we measure the phase, And we just see how the phase of the final qubit changes with respect to the frequency, which is just a measure of how separated the two states will be as we change the frequency. So the more the phase is changing very rapidly with the oscillation, the frequency we're trying to measure, then we're very sensitive. If it changes very slowly, we're less sensitive. And this is actually directly related to this Burris distance, and it's just a matter of a few lines of algebra to show the difference.
This Hamiltonian modulation is done with the flux.
So this Hamiltonian modulation is done with a, for the experts, we are using an AC star shift from an off-resonant drive, and we're just modulating that amplitude.
So you want to do it fast.
Yeah. So we're using 1 megahertz. So you could, it's easy, we're using 5 megahertz. So it'd be easy to use a flux from some relatively small coil. Okay, so here's the frequency sensitivity in this case. Okay, so we measure basically the slope. This tells us the frequency sensitivity, and so it's in units of the phase uncertainty. So you'd multiply this by the phase uncertainty we get from repeating the experiment many times to get the ultimate sensitivity. And you can see it decreases, and it decreases like 1 over t until things start to get worse. That is, our sensitivity is not as good. And this is because the qubit has a finite t2 time, so that as time progresses, you can think about the block vectors are shortening, so the overlap starts to increase. So that the t2 time happened to be quite short. It's like 4 microseconds. So you can see at 4 microseconds, we're already doing, a factor of 2 worse than the limit we should expect.
So this x-axis is the evolution time?
This is the evolution time. So this is like the Ramsey time. Okay. So now, let's try to do this control. This is the uncontrolled case. We know it should go like 1 over t. So what we're going to do the control is actually very simple. We just apply pi pulses right at the antinodes of the Hamiltonian, right where the derivative of the Hamiltonian crosses 0. We just need to change the eigenvalues, so we're basically going to change the eigenvalues right at that point. We're going to swap them. So the pulses they're like 10 nanosecond pi pulses. So they're very short compared to the period we're measuring, but actually we found that was rather insensitive. So 20, 30, 50 nanosecond pulses were fine.
Then do you start